Hello everyone, welcome to NK Chemistry Hall. Today we are going to be looking at the concept of acid and bases. We are going to be looking at the definitions of acid and bases for different concepts. We are going to be looking at the strength of acid and bases. And lastly, we are going to be looking at the acidity of a base and the basicity of an acid. Make sure you pay attention to this class, and if you have any questions, make sure you drop it in the comment section. Okay, we are going to be looking at the definitions of acid and base according to Arrhenius, according to Bronsted and Lowry, and according to Lewis. We need to pay attention to all these definitions because no single definition will give us a clear concept about acid and base. So the beauty of it is that the subsequent definition works on the limitation of the previous one, as we are going to see. So according to Arrhenius, Arrhenius defines an acid as any substance that increases the concentration of hydroxynium in water. So Arrhenius defines acid as any substance that increases the concentration of H3 plus of water, while he defines a base as any substance that increases the concentration of OH minus in water. So if we look at this equation, H2SO4 plus H2O, so that's going to give us H3O plus S minus. So as you can see, when H2SO4 is dissolved in water, it increases the concentration of H3 plus. The result is HCl plus H2O give us H3O plus Cl minus. So this is H3O plus. While a base, if I use sodium hydroxide as an example, NaOH, it gives us Na plus OH minus. Calcium hydroxide, Ca2 plus OH minus. So these are the hydroxide ions that are released when we result in aqueous solution. Now, one of the limitations of Arrhenius definitions is that it only restates the concept of acids to substances that produces H3O plus in aqueous solution. That means for it to be an acid, it must dissolve in aqueous solution to produce H3O plus. So substances like SO2, NO2, or aluminum chlorides are not regarded as acids according to Arrhenius. The same way, substances like ammonia are not regarded to as bases in Arrhenius definition. Okay, that's that about Arrhenius concept of acid and base. So let's look at Bronsted and Lowry. Bronsted and Lowry define acid as a protoether. So substances that emit protons, they are said to be photogenic, while it defines a base as a proton acceptor. So a base is a proton acceptor. Substances that accept protons, we refer to them as so a place is the photophilic agents. So we are going to look at this in some of these questions. Okay, a typical example is NH3 plus HCl to give NH4 plus Cl minus. So in this equation now, this HCl donates its electrons to NH3 because it's when it donates its electron, it loses this proton to become this. So this is our acid. Why ammonia will accept the hydrogen ion to become NH4 plus. So this is our base. Now, the concept of Bronsted and Lowry acid and base led to what we refer to as conjugate acid base pair. So conjugate acid base pair means that where this acid donates the proton to base, it will definitely lose the proton. So the subsequent substance or ion that is formed after the loss of this proton is about to be conjugate. So in this case now, this acid loses its H plus to NH3. So to become Cl minus. See, this Cl minus now is the conjugate base of this acid, whereas this NH4 plus is the conjugate acid to this base. To call this one conjugate acid. Another typical example is when we have ethanoic acid plus water. So this one will give us CH3COO minus plus H3O plus. So this is our acid. This is our base. So this donates its proton to this for this to become this. So this will be the conjugate acid of this. Why this loses its proton from this? So this will be our conjugate base. We also have examples on water reacting with another water molecule. So in this case now, we have H3O plus OH minus. So this is the same molecule of water, so we assume this is our acid and this is our base. So when this is our acid, this acid has donated its proton to this to become this. So this is our conjugate base of this acid. Why this base accepts this proton to become this. So this will be the conjugate acid is this. Now in this case, water is performing the role of an acid and a base. So we can say, we can refer to it as being amphibians. For the substances that can behave as an acid and can also behave as a base, we refer to them as amphicotic. Now the last one, we're going to be looking at definition of acid and base according to Lewis. Lewis defines an acid as an electron pair acetone, while a base is an electron pair group. Substances that accept electron pairs, we refer to them as electrophiles. While substances that donate the electron, we call them nucleophiles. So a Lewis acid is an electrophile, while a Lewis base is a nucleophile. So we are going to be looking at some examples of Lewis acid and base. So a typical example of Lewis acid and base is a reaction between ammonia and boron fluoride. Now, this will give us a complex. Now, in ammonia molecule, the central atom, which is ammonia, has, this is the structure of ammonia. 2, 3, 4, 5. So one of the hydrogen bond with ammonia here, one of the other hydrogen bond here, the other hydrogen bond here. So we have a lone pair of electron of the ammonia molecule. While in boron, we have this 1, 2, we have 2, 3. So this is one fluorine atom. This is another fluorine atom bond here. This is another fluorine atom bond here. So there is no electron here in this place. So this lone pair of electron that is here, that is on this ammonia, will be transferred to this boron fluoride. That has an empty electron pair. So in this space now, this is the donor. This is the donor. So this is the Lewis. Is why this is the acceptor. This is Lewis acid. So two of them will form a complex called sodium ammonia. Right, the complex. Okay. Another example is aluminum chloride plus chloride M. So in this case now, aluminium is 8 total echo, that's 2, 8, 3. 1, 2, 3. So chlorine, one of the chlorine will quite displace, the other chlorine will quite so there is an empty electron here, while a chloride ion, which is 2, 8, 8. Chloride ion means it has accept 1 electron, so from 287 becomes 2, 8, 8. So that means that the outermost electron has 4 8 electron. So this is AlCl2. Then one of these low pair of electron on this chloride molecule will be transferred to this empty electron sheet there. So now this is the donor. This will be the Lewis base. Why this is the acceptor? This will be the Lewis acid. So this is DLC L beta beta, and it is Cl minus right beta. So two of that will form AlCl3 CX. Should give us AlCl4 minus. Okay, we've looked at the definitions of acid and bases from different concepts, which I believe we understand clearly. So now we are going to look at the strengths of acids and bases. So an acid can be a strong acid or a weak acid. Same thing, a base can be a strong cold spring base. So the concept of strong acids or weak acids depends on the heat at which they release the hydrogen ion in water. So acids that are strong, they dissociate completely in water. The dissociation is about 99.9%. They dissociate completely in water, while weak acids dissociate partially in water. So one of the major way we can identify a very strong acid and a weak acid is by their acid dissociation constant. So we'll look at that in our subsequent class. So for a strong acid, the acid dissociation constant is usually greater than 7.1. But for a weak acid, the dissociation constant is always very low. Like for instance, ethanoic acid, the dissociation constant is about 1.8 times 10 raised to power minus 5. But you see that is very low. So acids that fall into these categories are H2SO4, HNO3, HCl4, HBl, HBr, and HI. So these are strong acids, while all other acids fall into the category of H2CO3, H3PO4. These are weak acids. So that dissociation constant is very small because they dissociate partially in water, while these ones they dissociate completely in water. So we can also classify bases into strong base and weak base. Bases that ionize completely in water are referred to as strong base, while the ones that ionize partially in water are referred to as weak base. Majorly, all bases of alkali metals, group metals, they are referred to as strong base, except francium. And the reason is because francium is radioactive. So bases like sodium hydroxide, lithium hydroxide, potassium hydroxide, what else do we have? And some bases in too, like magnesium hydroxide and calcium hydroxide. They all fall under strong bases. Why? Bases like ammonia, aluminium, and chloride. All these they are referred to as weak bases because they are ionize partially in water. Okay, lastly, we are going to be looking at the basicity or potosity of an acid and the acidity or hydrosity of a base. So the basicity of an acid refers to the number of replaceable hydrogen ion of an acid. That's the number of possible hydrogen ion that acid can give out to a base during an acid-base reaction. So we have acids that are basic, or you say they are monotic. You have acids that are dibasic, or you say they are diotic, and we have tribotic or tribasic acids. So acids that are monobasic or monotic, they only release one hydrogen ion in water. So a good example is HCl. HCl will dissociate to give us H plus because Cl minus. So it's releasing only one hydrogen ion. Another example is ethylic acid. So it's dissociate to give us CH3CO minus plus H plus. So if you look at it, that's about 4 hydrogen ion, 3 here, 1 here. But it's only giving out this aqueous solution. So that's why it is monobasic. Okay, for acids that are dibasic, they ionize to give out 2 hydrogen ions. So a good example is H2SO4. So H2SO4 will dissociate to give us H plus SO4 2 minus. So balance this. So this is 2 hydrogen ion. Another example is H2SO3. So this will dissociate to give us H plus SO3 2 minus. They are dibasic. While acids that are tribotic or tribasic dissociate in water to give 3 hydrogen ions. The real example is H3O4. So in this we have H plus EO4 equal minus. So to balance this reactor, so they are tribasic. Okay. Now let's look at the acidity or hydrosity of a base. The acidity or hydrosity of a base refers to the number of hydroxide ion, the numbers of NH minus ions that in base will remove aqueous solution. So we can also have monoacidic or monohydroxic base. It's called diacidic or dihydroxic. Then we have triacidic or triandromacic bases. So bases from the word mono, bases that are only release only one hydroxide ion in water. Typical example is sodium hydroxide. N in plus plus OH minus. Calcium hydroxide was K plus plus OH minus. So they are releasing only one hydroxide ion in water. Why ions like calcium hydroxide, Ca2 plus plus H minus. So to cancel this, we have to put 2. So this is dihydroxic. Substances like magnesium hydroxide. So you have Mg3 plus plus OH minus. So this is di. Why triacidic or trihydroxic bases are bases that ionize in water to give 3 hydroxide ions. A good example is OH2 aluminum nucleosides. That's Al3 plus OH minus. So to cancel this out, we have flat 3. For another example is iron 3 hydrogens. So Se3 plus OH minus. We have flat 3. So these are trihydroxic. These are di. Why these now, one beautiful thing about this is that the concept of basicity or protonicity of an acid will determine the kind of salts that such an acid can produce. We have different types of salts. We have normal salt, we have acid salt, we have basic salt. So in our subsequent classes, when we look at salts, we are going to look at how the basicity or protonicity of an acid, how it affects the kind of salts that each of these acids can produce. That will be the end for today's class. Don't forget to like, subscribe, and share our video to your friends that might also benefit from this class. If you have any questions or suggestions, drop it in the comment section. See you in our next class. Bye.